Okay, so last time we were talking about quantization. We started quantization in conformal gauge. We discussed some subtleties related to quantization. So today mostly we'll discuss quantization in light cone gauge, and then we'll get back to quantization in conformal gauge later on, maybe a couple of lectures later. So. So first we'll start with some small comments as to how to get to light cone gauge starting from conformal gauge. So in conformal gauge we fix the metric to be of diagonal form, right, with a proportional to the unit matrix kind of, and then we still have the residual conformal transformations that we can apply, an infinite dimensional group of conformal transformations left from diffeomorphisms. And we can use that to fix the gauge further. In principle, it's not a complete gauge fixing, right? We still have that freedom, and we can use that freedom to go back to light cone gauge. So how it works in practice is as follows. So suppose, we want to so this is just some kind of comment. In principle, we will later today we will just stick to light cone gauge and just stick with it. And but this is just useful for general understanding. So the equations of motion in conformal gauge are d plus d minus x mu equals 0, right? Where mu is from 0. Yeah, so that means that d plus. So now we'll look at x plus mu equals plus. So that means that d plus x plus equals f of x plus. I mean f of sigma plus. So sigma plus minus are worldsheet light cone coordinates. So they're proportional to tau plus minus sigma. Coefficient doesn't matter really. So d minus x plus is g of sigma minus, right? Just follows from this equation. So then let's make a reparameterization. Sigma plus goes to sigma tilde plus, and then dx plus over d sigma plus is and so this is some function of sigma plus, and we multiply it by another function of sigma plus. So ideally, we want to set it to a constant, therefore, by this transformation. So try dx plus dx plus over the sigma plus is whatever it is. And then we want to set dx plus over the sigma tilde plus to be a constant. So basically, we want to choose our x plus as the new sigma tilde plus. So this is possible, but the constant cannot really be chosen. So the constant is invariant. Same stuff like we discussed before. So we can't really fix the constant. The constant is what it is, because we're multiplying by this Jacobian, right? Well, our change of variables has to respect the boundary conditions. So, for example, periodicity, right? So that means that, say, sigma plus is sigma tilde plus some t of sigma tilde plus, where this is periodic. So the sigma plus over the sigma tilde plus is 1 plus t prime. So basically, because this coefficient is fixed here to be 1, we cannot change the zero mode of you can expand these guys in Fourier series, right? You're multiplying two Fourier series, but the leading term is 1.
What are we trying to do here?
We're trying to set this dx plus over the sigma plus to a constant. I mean, we're trying to get rid of as much functions as possible by using conformal reparameterizations. So changes, we go from sigma plus to sigma tilde plus, and we want to ask how can we simplify our gauge. I mean, can we further simplify the gauge? I mean, in principle, we want to set, remember the light cone gauge, that x plus equals tau. I mean, that's what we want to do. I mean, we want to get back to the, we want to get here using this kind of transformations. So of course that means that derivatives are constants, right? So that's what we're doing. And in particular, we want to set dx plus over d sigma plus to a constant and dx plus over d sigma minus to a constant, right? Because tau is kind of sigma plus plus sigma minus. Again, with some constant, which I will not keep track of these normalization factors here. I'm saying that yes, we can set it to a constant, but this not an arbitrary constant. The constant is what it is, because the reparameterizations there's some restriction on these reparameterizations that their leading term is linear and with coefficient 1, right? This is due to the fact that sigma plus has period 2 pi and this guy has period 2 pi, right? And this is periodic. There is no other choice you can make, right? If you put a coefficient here, it will not be 2 pi, it will not shift by 2 pi. So, okay, so the point is that doing this, we can set dx plus over d sigma tilde plus to a constant, and accordingly, dx plus over derivative with respect to the other variable to a constant 2, right? Some other constant. By using sigma minus equals sigma tilde minus plus t tilde. So then you can get here. Right, this is just another version of the same argument we've used already many times, basically. Doing these reparameterizations and seeing how various quantities change under these reparameterizations, right? For example, when we were imposing light cone gauge, we were doing just reparameterizing sigmas and seeing that something is multiplied by Jacobian of sigma, right? Here we're reparameterizing sigma plus and sigma minus. So it follows from these two guys that x plus dot, which is proportional to, okay, let's just write that it's equal to d plus d minus x plus. So this is a plus b x plus prime, which is equal to d plus minus d minus equals a minus b. So this means that the solution is x plus equals a plus b tau So x plus has to be periodic also, because I mean let's assume we're dealing with closed case. I mean with open case you can somehow deal accordingly. well, open case will not really differ. So in the periodic case, x plus has to be periodic, so A has to be equal to B, right? In the open case, the derivative of this has to be 0, so that gives the same answer, right? So so if Neumann anyway, A is equal to B. So this is one case. Another case. So that means that x plus is 2a tau, right? Which is almost what we want. Well, there's some coefficient, 2a, but right, we said both derivatives with respect to sigma plus, sigma minus two constants. That means that derivatives with respect to time and space are constants. But also because of boundary conditions, these constants are related. So then we get here, which is almost the light cone gauge. And A is a constant that can be related to, sorry for the non-standard kind of path around the blackboard, where circle of life. The P plus is so P plus, recall what is P plus. P plus is minus T integral x plus dot d sigma 0 to 2 pi. So this is minus 4 pi AT. So A is minus P plus over 4 pi t. So that means that x plus is minus P plus over 2 pi t tau. So this is where we can get by doing these reparameterizations. So this is almost the light cone gauge that we had earlier, up to a small reparameterization of tau. So there's no problem with that. That just means that actually in conformal gauge we kind of used one more degree of freedom, and already by imposing conformal gauge, and that's why we cannot fix this coefficient now to 1. But we could do, of course, rescale tau by this constant, and then we'd get here. So if you rescale tau, right, okay. So this is how, so if you have some solution of equations of motion in conformal gauge, you can do this procedure and find the form of solutions in light cone gauge. Okay, yeah, I mean, this is the boring part, kind of. Yes, I agree, but I mean, this is like an inevitable. So I mean, we've done this kind of transformations a few times, so it's almost repeating itself. But we should nevertheless discuss that. Okay, and so now let's look what happens to the Virasoro constraints, right? So Virasoro constraints, of course. We'll simplify and so this is 0. And now this is, oops, wait. So 6 plus, 6 minus. So this is A, so which is minus p plus 4 pi t. And so you can solve for d plus x minus. So and you can solve for x minus, same for d minus, x minus. So this can be solved for x minus. Okay, and actually we'll solve for x minus explicitly soon, but not immediately. So you can resolve the constraints just like as we normally do in light cone gauge. Okay, so now let's really perform the quantization in light cone gauge as was announced in the title. So quantization means we replace Poisson brackets with commutators, and so here A and B, they range from 2 to d minus 1. Well, recall the formula for, well, the main formula we derived in classical theory was the mass formula for the open and closed string, right? So the square of mass as a function of the oscillators. So in the open case, this is 2 pi t. Some this was this formula, well, the obvious question that arises is the ordering issue here, right? Related to the ordering issue. So those oscillators, they do not commute. So we can have some normal ordering constant. There is no real, at this point, there is no real resolution of this. So one naive option would be to do symmetric ordering or while ordering, right? So I mean, why not do things in a symmetric way? Then this is actually how it's done in the usual harmonic oscillator. Yes. So in usual harmonic oscillator, we replace the A star A with 1/2 A dagger A plus A dagger, right? Which is A dagger A plus 1/2. That's how we get the famous 1/2 shift of the oscillator. So we could do this here. This would give us. So if maybe that's right. So 2 pi t sum So the ones with the oscillators with positive ends are the annihilation operators. The one with negative ends are the creation operators. So that means that we've defined actually some Fock space, some vacuum state, which is annihilated by all annihilation operators. Right. So then we do the same reordering as we did here, and this would give alpha minus NA plus 1/2. Oh, so sorry, I mean plus 1/2 n, right? N because there is an n here. So what's the problem with this? Why is this worse than this?
Is it divergent?
Yeah, because we have an infinite number of these oscillators, and we're summing n from 1 to infinity, right?
It means we can ignore it.
That's a negligent kind of option, but I mean, yeah, you shouldn't ignore it. I mean, yeah, and yeah, okay. So so then we have here a sum, 2 pi t. So there's nothing wrong with the first term, right? It's just sum of oscillators. It's still an infinite sum, but that's not a problem because we're always we can always just consider states with a finite number of creation operators, and then this guy will always give finite answer. But then we have this 1/2 d minus 2 times sum of n. So yeah, it's a divergent piece.
Can I ask a question? Isn't the sum already normal ordered? The one we had in the beginning for the mass of the orchestra?
Sorry, which one? You mean this one?
Yes.
No, I mean this was a classical expression, right? So
We need to
there's no real way to go around it. I mean, there's nothing that tells us what the ordering should be.
Can you keep it? Can you just say this is the new quantized form?
No, we'll see in what follows that the theory will not be kind of consistent you really have to choose this constant correctly. I mean, appropriately. Yeah. I mean, if there was no further constraints on the system, I mean, no other requirements, then yeah, of course, it's up to you what constant you choose. I mean, there's no real reason to choose one ordering over the other. But here there are some further constraints. You know, so for example, if you have a system with symmetries, you typically want to require that the symmetries are preserved upon quantization, and that sometimes resolves this kind of ambiguities. So say your algebras work correctly. So suppose you have some algebra, Lie algebra behind it, yes? And you want that the classical Lie algebra transforms into the same Lie algebra upon quantization. And that's not obvious because of these ambiguities. And that's exactly what happens here. Some question?
How you wrote this expression?
This one? No, I mean, I just rewrite this stuff, right? I've swapped computed these oscillators, these ones, using this commutation relation, and then I just well, there is a sum over A from 2 to d minus 1 Nothing depends on A here, so it's just D minus 2, right? It's just a sum of ones from A equals to 2 to D minus 1. So that just gives you D minus 2 factor, just an overall factor. It's just an overall number of these guys with respect to the upper index.
So you do some binomial expansion?
No binomial expansion. I mean, this is just trivial rewriting. I mean, it's the same formula, right? There is an 1/2 n here. There's 1/2. Sorry, I mean there's an n here, right? I mean maybe that's your question. I mean, it's just a trivial rewriting of this. Okay, and well, this is divergent, so it's unclear what to do with it. One popular thing that people do with such sums, at least in quantum field theory, is what is called zeta function regularization. So that means, I mean, that's a regularization just like any other, but that means we just replace the sum by a zeta function and evaluate it at the relevant point, right? That's a clever thing, right? So I mean, you just replace this with zeta of s, which is sum 1 over n to the s. And then the sum is zeta of minus 1, right? So when is this sum convergent for what?
Real s bigger than 1? Real of s?
Yeah, that's right. Yeah, that's right. And what do we do at other values of s?
We can analytically continue.
Yes, exactly. We can analytically continue. So that's the idea. The fact that the sum diverges doesn't mean that, you know, the zeta doesn't exist for other values of s. And well, actually, technically, you just use the formula that so-called Riemann relation to analytically continue, which is zeta of s 2 to the s y to the s minus 1 gamma 1 minus s times zeta of 1 minus s. So we want to evaluate zeta of minus 1. So this relates this to zeta of 2, which we know. So here zeta of minus 1 is whatever it is. And then there's zeta of 2, which is pi squared over 6. Right? All even values of zeta, positive even values, are expressed to pi's, right? Factors of pi. So then you derive that zeta of minus 1 is minus 1/12. No, 1/24. Yeah, you derive whatever you derive. I mean, but this guy will be minus 1/24, d minus 2. Yeah, so zeta of minus 1 is minus 1/12. Right? Hope it's all correct. So this gives you some kind of answer for this sum. Then you have this double sum. So this is normal order now, right? This is the answer you get. Of course, this is not a derivation of any kind, just some ad hoc prescription. But we'll see that ultimately this actually gives the right answer. So that's why it's worth mentioning. Okay, so that's some formula for the masses of the quantized string. And now the point is that if classically these masses were had a continuum spectrum, right? Alphas were just some numbers. Here, this thing will be quantized, just like in the harmonic oscillator, in the quantum harmonic oscillator, right? And as a result, the spectrum will be discrete. Okay. So so we've already defined before the Fock space vacuum here. What we've actually hidden here is the dependence on momentum, right? We also have the momentum. We have the pair x and p. Apart from those layers, we have the x and p, and we have some Hilbert space associated to that. X and p are some operators also acting in some Hilbert space, right? Not just the Fock space of oscillators. And so we actually, in reality, we have this kind of vacuum state. So this is still annihilated by all the positive oscillators, but then the P A acting on this gives Q. So it's also an eigenstate of momentum. And in fact, we also have the one more commutation relation, which was x minus with p minus equals I. Right? We still have that remaining mode. You were asking about that. We still have this one extra mode. So we have this transverse momenta, and we have this p minus, this q minus, 0q. And q plus is determined from the, q plus is proportional to the m squared open.
So here shouldn't be our PA eigenvalue should not be 0 because our energy is 0 in our lowest energy state.
No, you see the energy has there is a so when I say m squared open, I meant that I put all the transverse momenta here, right? So I mean q plus is p squared plus m squared open, right? That's the I mean, you see, this really depends on what you mean by energy. Here, by actual Hamiltonian, we actually define as this m squared as our Hamiltonian. Or, if you like, you could define the worldsheet Hamiltonian is p plus, which was, like I said, m squared open plus pa squared, basically, right? So indeed, if you set all momenta to 0, pa squared will be 0. But there is still contribution from the mass. It's like rest mass, like in relativistic theory, right? The rest mass gives you non-zero energy, equal to the mass, kind of like that. So there is. I'm saying it's not just a free particle moving, but it has some additional contribution from the oscillating modes of it, which make sure that which contribute to the energy. So this zero, the first 0 refers to the oscillator occupation number, and Q refers to the eigenvalue of momentum. Right? I mean, we have momentum commutes with the oscillators, so we have a product, tensor product of Hilbert spaces.
So your momentum is 3 momentum.
Well, it's d minus 2 momentum, d minus 1 momentum, right? well, d minus 2 and this guy, so d minus 1 kind of momentum. And this component of the momentum is expressed through the dispersion relation, right? Relativistic dispersion relation, that p squared plus m squared is 0. That's p plus. P plus can be expressed from via p minus, pa, and the mass. So, okay, so so what was I gonna say? Okay, so we have this this Hilbert space, and yeah, well, of course, on top of this, we can act on our vacuum with the raising operators. So we could have general state. Is so you have this vacuum. So okay, you have alpha minus 1 a1, alpha minus 1 a n1, alpha minus 2 b1, bn2, alpha minus 3 c1, all of these guys acting on the on this state. So the Hilbert space is the span of such states. And superposition with respect to momentum states. So momentum is a continuous spectrum, has a continuous spectrum. So the next question is yeah, really checking the algebra, as we mentioned before. So the algebra that we need to check is the Lorentz algebra. So the question is, does this theory have Lorentz symmetry? Lorentz symmetry algebra. So, well, why is this question reasonable? Because, well, we are doing it in light cone gauge, so we've broken part of the Lorentz symmetry, right? And so we want to check that ultimately it's still there. So I remind you how Lorentz symmetry works. I mean, this is the such that mu and these are the Lorentz transformations. And so by Noether's theorem, you derive the Lorentz generators. So this is Noether's theorem. So basically, ultimately, we want to discuss. So we have this Hilbert space, rather complicated, as we shall see, and we want to know how Lorentz symmetry acts in this Hilbert space. That's ultimately what we want to know, because you see all these indices, they are indices of SO d minus 2 rotations in d minus 2 transverse coordinates, right? And we want to have rotations in d coordinates in principle. I mean, the full Lorentz algebra, time and space. So to this end, we have to recall how the Lorentz generators look like to start with. So Noether's theorem says this, and where L mu integral to pi And well, we want to check that it satisfies the Lorentz Lie algebra. So, so 1D minus 1 algebra looks as follows. That so this is a okay, I'll write that later. Yeah. So here, so this is the Lorentz algebra. L's are just the abstract generators of this algebra. So these are generators. And we'd like to look at those generators related to the light cone directions, right? Because the transverse directions, they will work pretty easily. So the ones that are might be not so trivial are the ones that involve the light cone directions. That means plus and minus. So we need the generators that have plus and minus indices. So in particular, if we set, so we find that L plus I, L plus J is 0. And this is the same as L minus I, L minus J. Right? So we have, so the generators, they are, they can be split as LAB, L plus, yeah, maybe I'll use Roman capital letters as before. So LAB, L plus A, L minus A, and L plus minus. Right? This is the split with respect to the SOD minus 2 algebra. Okay, and let's check how those generators look like from the point of view of our worldsheet theory. So now in place of small l's, we wish to put capital L's and see what happens. For example, L plus A is the integral over tau PA minus xj P plus. So that means that this is tau PA minus XA P plus. And so now we can compute the derivative over time. So we differentiate. So there is explicit time dependence here. So this is PA plus worldsheet Hamiltonian, maybe I here, and so this is PA minus P plus times PA over p plus. So this is 0. I mean, this you get by explicitly commuting commuting with the Hamiltonian. So the only thing here that does not commute with the Hamiltonian is this x here, right? Hamiltonian has Hamiltonian is well, pa squared plus m squared, right? So x doesn't commute with p. There will be a factor of pa coming from there. So there's nothing funny going on here. Right, we're just checking that those guys are still conserved charges quantum mechanically. So when we put commutators everywhere. But when we look at L minus A, it will be a much more complicated thing. Why? Because what is L minus A? Yeah, okay, and also let's check that before we go to L minus A, let's check that an easy calculation shows that the L plus A over L plus B is, yeah, it has, you see there's only P and X that do not commute. So there are some terms, some elementary terms, tau P plus commutator PA with XB minus tau P plus commutator of X, XA with PB. So this is minus I delta AB, this is plus I delta AB, so this is 0. So it's a easy calculation that shows that they commute. But when we go to L minus A, it's a much more complicated thing. So L minus A is, yeah, by the way, I should write everywhere that it's maybe approximately equal. I'll explain what I mean by that. Okay, so typically the generators will involve sums over oscillators. Because let's look at basically any random, say, LAB generator. LAB, it has XA, PB here. We insert the expansion of X and P into modes. They are linear in the oscillators, so you'll get some quadratic thing in the oscillators. The exception, this was an exception, because here we fixed, this is related to gauge choice, right? These guys have no oscillators in them. But typically we'll have expansions of this form. But as opposed to these LAB generators, which are quadratic in the oscillators, this one is actually cubic in the oscillators. Why? Because actually alpha n minus is not, we didn't have such oscillator before, right? It's just a shorthand notation. So I have to explain what is alpha n minus here. So before I explain what is alpha n minus, maybe let's mention, I should also explain what it means, what the approximate, the equal here means. So the point is that these guys also suffer from ordering ambiguity, right? So for example, these x's and p's, they do not commute. And same here, for example. So what we want to have is a Hermitian operator. So we can just order them symmetrically, and this will give us a Hermitian operator, right? So actually, in place of these guys, I should write 1/2, and their half sum of this, like x minus pa plus pa x minus. That would be Hermitian, right? Because upon Hermitian conjugation, the two operators are swapped, right? So, but why I write it this way here is because this will not affect our calculations. So the ambiguity, this ambiguity that arises, doesn't matter for our particular calculations. So for example, here, the commutator of xa with p minus is minus pa over p minus. Okay. X minus pa is 0. Then x minus with p minus is minus I p minus with p minus. Then, as I already mentioned, x minus with p minus is I. And all the other commutators we've already mentioned before. So kind of homework is to derive this. Right, p minus, where the minus is upstairs, is essentially our worldsheet Hamiltonian. So it's a complicated function of all the variables. So you have to compute this with that function, and you will find this. Right. I mean, for example, here, remember that p minus was something like 1 over p minus times some pa squared plus m squared. Something like this, right? So when you commute with x minus, this differentiates this piece here, and that's why you get so because of this, there is some ordering ambiguities. These two just follow from the canonical commutation relations. This is just postulated when we quantize the system, right? That this x up or minus is the residual coordinate, and it has to commute with the other coordinates, the other momenta. So these you don't really have to derive, but I mean you have to derive these ones. These two are derived from the explicit expression for p minus upstairs. So yeah, it's true that there is a great deal of kind of technicality in these calculations, but there is no way to go around it. Okay, now I should explain what is alpha n minus. So what are the modes of the minus of x minus? I mean, these guys that enter here. So these are just formally the same, just the decomposition of x minus in oscillators. It's completely analogous to the decompositions we had before for all other coordinates. Okay, that's just a definition, if you like, of this alpha minus. But then this alpha minus is not an independent variable because we have the constraint that x minus prime equals minus 1 over p minus sum over pa right? So you can substitute here the expansions of x and p's in the Fourier series and read off the relation between all these variables to the variables in the right-hand side. Right? So I told you many times that x minus, we can solve this for x minus. So that means we can find the coefficients of the expansion in terms of the transverse coefficients, which are the, and as you see now that these coefficients will be quadratic in the transverse coefficients, right? So as a result, we find that alpha n minus is square root of pi t over 2. We will put normal ordering here. And so n also belongs to Z. Okay, so I mean you substitute here, you solve for alpha n minus, you get this.
Why did we use the normal ordering?
Why did we use the normal ordering? You see the alpha n minus here are defined only for n unequal to 0.
Oh, it was like the argument from last lecture, where we had like only a single term where it was.
Yeah. It only matters for alpha 0, which was not here. So actually, it's a reasonable question. Here I've added one more guy here, which I called alpha 0, secretly by writing that n is anything, right? It's my choice. I can define whatever I want. I mean, I just define it in normal or ordered way. I mean, it's just a new variable that we call alpha 0 that was not present here, but it will be just useful later on. Why? Because alpha n and alpha minus n will commute to alpha 0, just like in the last lecture. So it will commute to something, and we have to call that something some name. And we call it alpha 0, and I define it using normal ordering. I mean, you could as well add any constant and redefine it, but just no reason to do that. So here it's not the situation with ordering that we discussed before, where this was actually physical kind of problem. Here is just a definition, yeah. Okay, and as a result of this, these Q's are actually cubic and oscillators, right? So you see, LA plus had no oscillators whatsoever. LAB will always be quadratic and oscillators, but this guy is cubic and oscillators. So that's the most complicated one, which is why we study it. Okay, and yeah, so now we want to compute the commutator of so we want to compute those commutators of these cubic combinations of oscillators. And the first thing that we should ask is what can we expect from this calculation, right? Okay, so cubic, you compute in two cubic combinations of oscillators. So what kind of combinations of oscillators can you get as a result? What's the power of the oscillators that you expect? For example, I compute two oscillators, I get power 0, right? If I commute 3 with 3.
Oh,
Huh?
oh,
No, it's always, I mean, they always disappear in pairs, right?
Yeah.
So 3 plus 3 is 6. So it has to be even for sure. But I mean,
It's 4, I think.
yes, 4, because well, you commute at least one pair, you get 4, right? So you can get 4, you can get 2, you can get 0. But I mean, because you can commute them, you might have to commute them several times. A priori, you don't know. Yeah, but so yeah, here we will assume that classically nothing bad happens. So classically the commutator is 0. So the commutator should be 0 if we want to have Lorentz algebra, right? As we discussed. So in a way, let's maybe well, assume or check, assume that we have checked that classically the Poisson brackets are 0. In principle, as we discussed in kind of usual systems, this just follows from Noether's theorem. We discussed that Noether's theorem gives you a map from the Lie algebra to the two functions on your manifold, which is a homomorphism, Lie algebra homomorphism. If on functions you take the Poisson bracket as the Lie bracket. So that means that generators go to some functions that represent these generators, and their commutation, their Poisson brackets are exactly the same as the commutators of the original generators. So in the original algebra, the commutator is 0. So the Poisson bracket should be 0 by Noether's theorem. Of course, here it's a little bit more subtle system and so on, but you might check that it's still 0 classically. So if it's 0 classically, then what happens? What happens quantum mechanically? So when you compute the Poisson bracket of cubic guys, this will be exactly quartic, right? Because the Poisson bracket acts as derivative on each of the cubic pieces, so you will get quartic combinations in the end. But we say that classically this is 0. So that means that there is no quartic term in the commutator. Right? The argument is that the quartic term reproduces the classical quartic term. And if classically the whole thing is 0, there is no quartic term whatsoever. Okay, but and the quadratic terms and 0-order terms, they come from commutators. So you kind of compute the Poisson bracket, kind of keeping trace of where the operators stand, and then you have to commute them in quantum theory. So that's how the commutator works, right? The commutator is like the Poisson bracket, but when you are not allowed to swap the factors, and then you start swapping them to bring them to, say, normal form, and this will give you either second order or 0-order terms in oscillators. So so here there's no fourth order terms. And I mean, if you just try commuting these guys, these fourth order terms will be a mess. So I mean, this argument is very, very useful. So there are lots of fourth order terms which cancel. That's the point.
I'm sorry, I didn't understand the argument. Can you try again?
So the argument first is based on the assumption that the Poisson bracket is 0.
Okay.
Yeah. So then the highest terms in the commutator are exactly like the classical terms.
Okay.
Because the commutator, it acts exactly like the Poisson bracket, just that you're not allowed to permute the factors.
We're not permuting them when it's highest order terms.
Yes, but for highest order terms, it doesn't matter if you permute them or not, because the permutations give you lower order terms, right?
Okay.
It's like a quotient, like
Sure.
modulo lower
So
order
it's the
terms. Yeah, so it's the same.
And there's 0 in the classical case, and so they must be 0 in the
Yes, but the quadratic terms do not have to be 0 by this argument, because they come from permutations after u. Just like what we did for Virasoro algebra before, remember? The extra piece in Virasoro algebra came from permuting the oscillators, right? But in Virasoro algebra, there was just a... the same argument would work, saying that the quadratic terms are the same as in classical theory, for Virasoro, I mean. And the zeroth order terms come from quantum corrections.
And now we need to show that they also disappear.
Yes,
Okay.
that's right.
Am I right that generally we also add something called central charge term?
That's in the Virasoro algebra, yes, Virasoro algebra.
So why are not we using this here?
Well, because first of all, this is not a conformal gauge where we have conformal symmetry. So in principle, conformal symmetry has nothing to do with a light cone formulation. And secondly, we're not commuting first of all, we're not commuting the generators of the conformal algebra. So why would we get central charge? I mean, central charge is for the conformal algebra. We're commuting Lorentz algebra generators. So this is some target space symmetry, right? And also by going to light cone gauge, by setting your, say, x plus equal to tau, you're explicitly breaking conformal invariance, even if you had any. Right? You no longer have any reparameterizations. That's what we're talking about in the beginning of the lecture, that we actually use all the remaining conformal transformations to go to light cone gauge. So here, forget about conformal symmetry here in light cone formulation. I'm just saying that technically it's similar calculations as we had for the Virasoro algebra, right? We could have the same argument last time, right? We were commuting quadratic operators quadratic in the oscillators, and what we expect to have is therefore by the same token is that either quadratic or lower order terms, right? And the quadratic term has to be the same as in classical theory. This was remember we had Lm with Ln equals m minus n. Lm plus n plus constant term, right? I mean, plus 0th order. So this was the classical algebra. And the 0th order term was because we were commuting the oscillators. So we'll do the same thing here, but now the highest term is 4th order term, which has to vanish. And the 2nd order term is like this 0th order term, which we have to compute. So then what do we expect? How can this guy look like? So this has to be 1 over p plus squared sum over delta m minus alpha minus mb So this is our ansatz for the answer. So where does it come from? So delta m are unknown is an unknown function of m. Where does it come from? Well, this guy has to be antisymmetric with respect to a and b. Also this guy commutes with alpha 0. Alpha 0. You were asking why we need alpha 0. For example, alpha 0 is kind of you could think of it as a grading operator, right? Which tells us the level of each operator.
Okay.
So for example, if we had here minus m plus 1.
So like this is a shift or something.
Yeah, so for example, if you have minus m times alpha m plus 1, if you commute this with alpha 0, it will be an eigenvalue of eigenvector of alpha 0 with eigenvalue 1. It's like a particle number operator, if you like, yeah? And this is particle number 0, because there's exactly the same number of negative and positive oscillator. And the same thing for LAs, right? they're of level 0, kind of. So their commutator also has to be of level 0, so it can only be have such terms without any shift of it, the index. And then it has to be antisymmetric with respect to A and B. So basically, that's the only thing you can write. Where does this prefactor p plus squared come from? I mean, it's also fixed by something. People are nicely sleeping. Peacefully. So it comes from the Lorentz symmetry, right? Then I remind you, there is also the L plus minus generator, right? This is the generator of Lorentz transformations in 0, 1 directions. So this is a two-dimensional Lorentz group in 2 dimensions, in R11. Right? What is the Lorentz group in R11? R11, Lorentz symmetry. This is important to know. I mean, this is the most elementary Lorentz transformation you can have, right? I mean, maybe you remember you remember rotation matrices, right? Like cos phi, sin phi, right? Huh? Okay, that's a fancy name for this matrix, yes. So I mean, this is like this, right? Something like this, right? But that's not the answer to the question. I mean, the answer is that this is just so this is SO11, right? And this is just R star. Maybe I should put plus here. I don't want to get into those issues. But I don't care about any kind of components disconnected from identity. I mean, I just mean the bulk of the Lorentz group. Why is that so? Because actually you can diagonalize this matrix, and this will be e to the eta, e to the minus eta. Again, why is this so? Because your line element is just d sigma plus, d sigma minus. And this is preserved by sigma plus goes to lambda sigma plus, sigma minus goes to lambda inverse sigma minus. Okay? So that's it. This is the Lorentz group in 2 dimensions. So this Lorentz group, I mean, its generator is this guy, L plus minus. Right? It's 1 dimensional, of course. So we should look at how the left-hand side transforms under this thing. And well, you should basically you will find out that this is multiplied by lambda basically. When you do this rescaling of coordinates, this L minus is multiplied by lambda. Well, just because basically L minus is x minus PA, right? So x minus is multiplied by lambda, so L minus is multiplied by lambda. So this guy is multiplied by lambda squared, right? And these guys are neutral under this transformation because they're transverse coordinates. So you have to have this factor compensates for gives you the right transformation property. So this is multiplied by 1 over lambda. And as a result, you have the right transformation with respect to L plus minus, okay? So this gives you the correct transformation property with respect to L plus minus. This gives you correct transformation property with respect to AB, so SO d minus 2. Okay, so that's why we have this ansatz for our answer. And what remains is to compute to compute delta m. So we want to compute delta m now. How do we do that? How do we compute delta m from here? We know that we have some expression of this kind. How do we find the coefficient? So suppose you have some function of a dagger and a, and you know this is delta times a dagger a in harmonic oscillators. How do you find this delta? If you know f, what should you do? I mean, of course, you can kind of commute it and bring to this form, but that's like doing the whole calculation again. We want just one delta. So the answer is that you just compute the matrix element, right? Basically, this delta is just a single matrix element. So you know you just need one matrix element. So if you need one matrix element, you don't need to compute the whole thing, right? The whole matrix. And the matrix element is just right? This is equal to delta, right? So we'll do the same thing there. So there we need the matrix element. And if you plug this in the right-hand side, you get k squared over p plus squared delta k times delta so this I get by computing the matrix element of this. So now we have to compute this matrix element and read off delta k. K squared comes from the fact that our oscillators commute to k. I mean, the commutator is k, right, not 1. So one needs to compute this matrix element. You see, actually, yeah, I even prefer to act with states of momentum 0. I can choose any momentum, but I prefer to choose momentum 0 because that's the easiest one. And so the calculation has several steps. So we want to act with LA minus. You see, we want to act with LA minus on this state. And then we get minus P minus XA minus QA minus alpha minus KD, where now P minus is minus pi t over P small minus K minus A. Yeah, by the way, I'm not sure I said what is A. So in that formula for the mass, right, we have the formula for the mass, which was 2 pi t L minus A. Right. L is the level, sum of oscillator, these quadratic combinations of oscillators. Minus A is a normal ordering constant, which we now set to arbitrary value. We calculate using zeta function of minus 1. This was 1. But now let's do a more honest calculation. Let's just set it to arbitrary value. So arbitrary
we got 1 when we set d to 26. But that was a formula which depends on...
Oh, yeah. Sorry. No, we didn't set to 26. You're right. We got minus d minus 2 over 24, yes. Okay. Yes. D equal to 26 will be a result of this calculation that we're doing now. So and a equal to this value will also be a result of this calculation. So now we don't assume this. Yes, okay. Just a is arbitrary, which is actually the right thing we should do. We should, anytime you have some normal ordering ambiguity, the right thing, you just say it gives some arbitrary thing and then see if something constrains it. So this is just by definition of L. And Q, so you compute how Q acts on this state. So that's not very difficult. K times plus I delta AD minus K minus. Okay, that's an explicit calculation. So you act with this Q, which is cubic on the oscillators, on the one particle state, and you get these quadratic combinations. Well, we do this because once we compute this action, the commutator is basically just overlap of the states, right? So basically, then we can compute LB minus alpha minus KC times L minus alpha minus KD. So this is just one half of this. And the commutator is when you then interchange A and B and subtract. So basically all you need to compute is this state. And for this state we have this formula. Okay, so then you compute this guy. You need to compute, it will ultimately reduce to a matrix element of 4 oscillators, right? There are 2 oscillators in each of these guys. So matrix element of 4 oscillators, that's in principle something you can compute in courses of quantum mechanics. So I'll just write a few formulas that we need for that. And then I'll write the answer. Formulas. So we need the matrix element of minus times, it will always involve this sum, 1 over IN minus NA alpha n minus K D minus I square root of pi T delta AD times K. So this is the first formula. Then the second formula is this is sum from 1 to K minus 1 and minus K over N delta AB and the third formula is alpha K minus from minus K minus is pi T T minus 2 over 12 K cubed minus K. So these are just various matrix elements that you need. And you also need the commutator of XB is QA minus, which has the form 1 over P minus sum 1 over N. I think maybe with IN, I think. K alpha minus N A alpha N B minus alpha minus N B alpha N A. Okay, these are just supplementary formulas that you need in this calculation because there are several cross terms here. You see this guy is a sum of 3 terms, this one, and this one. You multiply by another such guy, so there are some various cross terms. So in principle, you can restore all of them from here. These are all the commutators you need. And as a result, you get that delta k is pi t over 4 k plus 1 over k over 12 plus twice so that's the upshot of the calculation. So there are two kind of independent terms. One that goes linearly with k, the other inverse, k inverse. And so if we want to have Lorentz symmetry, so we must require that the commutator of these guys of L plus LA minus and LB minus is 0, so require delta k to vanish. For all k. So that gives you d equals 26 and a equal 1. So secretly we come to the same answer we had there somehow. So that means that this light cone, at least this light cone theory, that actually loses Lorentz invariance unless we're in dimension 26. Means 1 time 25 space-time directions. A should be equal to 1. So A equal to 1 is important because it enters the mass formula for the mass of our states. So next time we'll discuss that this actually naturally has Regge trajectories in this formula, right? Same that we discussed in the Vincenzo amplitude first time. And this A is related to the intercept of the Regge trajectory. So this is called a critical dimension for the bosonic string. And I mean, we did all of this for the open string. For closed string, you have also these alpha tildes, but it will lead to the same answer.
Sorry, I didn't understand how we got 26 here, 18.
No, we set delta k to 0 for all k.
Yes, from that we are getting d equal to 26.
Yes,
but here how we got ak as how we have 26.
You mean by how we got this formula?
Yes.
Well, yeah, it's just calculation. So you see, this is lengthy enough. I mean, this writing out this matrix elements. So then you plug this into this formula, right? So this formula gives you the matrix element of LB minus, LA minus. This involves, you see, you use this formula, plug this Q here, then you compute this matrix element. To compute this matrix element, you need all of these formulas here. And then you anti-symmetrize with respect to A and B. So you subtract 2 such pieces. And that I showed just on the previous slide, kind of, that this is equal to delta k up to some factor. This matrix element is equal to delta k. Yeah. So we read the delta k that we find is just this. So I mean, it's just a long calculation where you have to be very careful about various.
Isn't this strange that it works, the trick with the zeta function? I'm sure we can find other functions which analytically continue.
Yeah.
Is this an accident, or does that mean
Yeah, well, I don't know a deep explanation of why it works. This was just, I don't insist on using this trick. I mean, this is just for entertainment reasons. But yeah, somehow in many calculations in quantum field theory, it's a kind of a handy regularization, yes. Okay, so that's the upshot of this lecture, that kind of for self-consistency, this has to be in dimension 26, and the intercept of this Regge trajectory is also fixed. We will discuss it next time, why it's an intercept of the Regge trajectory. But I mean, this has important consequences for the whole business. And later in conformal gauge, it becomes somewhat more illuminating how this, how the critical dimension arises. Here it's just a result of this long calculation, basically.